A very short one-question homework assignment that we're going to do today.
It's due on Wednesday.
Yeah, that one's doing. It's short. This is
So,
it.
like, I
It's
saw
one
it
page.
and I was like,
I know. That's why I'm
that
going
makes
over it.
sense now.
Yeah, it's gonna make sense. But we're gonna. I don't want you to have it yet because I want you to take notes and then use that to do your homework assignment. And we'll have time to do that today. It should be fine. And then on Wednesday, we are going to have lecture about predator-prey models and interactions. And then I'm going to give you your last homework assignment. And I did put that on Wednesday, after Thanksgiving, right? Did you check the due date on that
I
one?
didn't check the one.
Okay, I'm pretty
I
sure I
just
put
saw
it.
the one where it was due
My,
like tomorrow or Wednesday, and I was just like, we have homework due on Wednesday too.
yeah, you do.
It's one question. That's,
It's one question.
I was expecting like.
It won't take long. Yeah, no.
That's not normal.
No. The point is to get you to draw the model again. And so the reason I'm going ahead and giving that homework assignment this Wednesday is I sat down to look how many Wednesdays we have left, and we only have 2. And so we need to do it in time to have it done so I can grade it before you have your exam, right? So we're going to start it on Wednesday. There is one question that I left on it that we won't get into until after Thanksgiving. Okay, so you're not going to be able to turn it in immediately. But I would, as always, suggest that you start to work on it. It will have life tables, exponential growth problems, logistic growth problems, this problem again, I think, and then of course the one that we're not going to get to. Okay, so it's a good one. Should get you ready for the final. And I'm pretty sure I put that due Wednesday after Thanksgiving, which is our last day of class. And then our final exam is 7:40 a.m. on Monday. Woo! Which we get done on Wednesday, so I guess if anybody has to have 7:45, and most logical to do ours, right? That kind of thing. Any questions about that? You do have a homework assignment due today, which is the one we did last Wednesday. Some of you have turned it in. I didn't keep count, so I feel like a few of you probably have it. So get it turned in by midnight today. All right. So today we are going to work with a model. We're going to start out in PowerPoint, and then I'm going to go to the board and draw it. It's going to be kind of similar in technique to what we did last week with logistic growth. So it's a process type of model. I don't think it's that hard. If you understood what we did last week, it should be good this week. Specifically, this whole PowerPoint is mostly about predator-prey interactions. And we've talked about predation as being plus minus, and that it's positive for the predator, it's minus for the prey. And the main definition here is somebody has to die, right? That's a good Monday morning thing. Somebody has to die. There are different types. So there's carnivory, where one animal kills and eats another animal. That's pretty much, if you ask like a grade school kid, they're probably going to give you an example of carnivory if you ask them about predation. There's parasitoidism, which I told you was really weird. We watched a couple of videos about it. But in the end, somebody dies, and so it falls under predation. Herbivory, we said herbivory can be predation if you actually kill the individual. Seed predators be an excellent example. And then there's one we haven't talked about, but we will before the end of this PowerPoint, and that's cannibalism. That should be a fun topic, right? And so cannibalism is where the predator and the prey are the same species. And it happens quite a lot. So we're going to talk about why it happens and the impact on the population. So we'll talk about that briefly. But we're not going to do types of predation today. We've really already covered the first 3 anyway. What we're going to focus on is the modeling today. And then we'll focus more on experiments about the modeling, and then adaptations of predators and adaptations of prey on Wednesday. All right. So we're still doing what are called Lotka-Volterra population modeling. And when they put together their competition models, which was our theme last week, they also put together some predator-prey models. As we look at the predator-prey models, they are going to look a little bit more different from our logistic growth models than the competition ones did. And so the competition models, you pretty much have the logistic growth intact, right? And then we just put our competition variables on the end. These are going to be a little bit different from that, but all of the aspects of logistic growth will still be there, all right? And so what's going to happen in our predator-prey models is we're going to have the population growing logistically constrained by whether they're being eaten by the predator or whether the predator is being successful in eating prey. Okay, that's the only constraint we're going to have for the most part. So I guess I should back up. It's really more we're modifying the exponential growth part. not so much the logistic growth part, because the competition's just not in there. It's just predator-prey models. And so after we work with our predator-prey models today, one of the things we'll talk about are problems with it. We'll do that on Wednesday. And one of the problems is it doesn't account for other things affecting their population like competition. Right? It just is kind of focused entirely on predator-prey interactions. Kind of like I talked about last week when we did competition, you need a model for each species involved in the interaction. So last week we had a model for N1, which was species 1, and a model for N2, which was species 2. And we said that if we wanted to add more species to the model, we would just keep going N3, N4, N5, and so forth. And so that's going to be the same today. What we're going to do is stay with 2 species to keep it simple, of course. And so we're going to have one model, which is going to be N-pred, P-R-E-D, that will represent the predator. And then we're going to have a second model that's going to be N-prey. Yeah, N-prey to represent the prey. Okay, so that's what we're going to do. So one model representing what's going to happen to the predator's population, and one model that's going to tell us what's happening to the prey population. And it looks like for my preview we're going to do prey first. So let's get into it. All right, so here's the prey model. And so instead of using 1s and 2s, we're using prey and predator, and you see both prey and pred in this model. So you want to be careful, make sure you do your Y's and D's correctly. And as you're looking at the model, the first part of it should look familiar because that represents exponential growth. So you have dn over dt equals rn. That's exponential growth, right? So dn prey over dt equals r prey n prey represents the population growing as if it is in an unlimited environment. And so the new part is after that in this model. So we have C, N-pred, N-prey. So we need to know what those are. We know what N-pred is, that's the population size of the predator. We know what N-prey is, that's the population size of the prey. So really it's the C that's important. And this is basically the efficiency of the predator, specifically how well and at what rate it's capturing prey. So how many prey are they taking out of the population, basically? That's what the C is going to be. And so we put all of this together. So we put the efficiency of the predator together with the population size of the predator and the population size of the prey, because how many prey are going to be taken is going to be related to how efficient the predator is, but also how many there are. Right? If you just have one predator in your environment and it's very efficient, it's going to take less individuals than if you have 100 very efficient predators in your environment, right? And so we got to take into account the number. And then the prey, number of prey, is also going to influence the predator. And so if we have a whole bunch of prey running around, it's going to be easier for the predator to find them. If prey becomes scarce, then it's going to be harder for the predator to find them. And so that's why we are constraining the predator efficiency based on the size of the predator population and the size of the prey population. Okay. Did y'all follow all that? Okay. And so this pop model, just to be complete here, this model assumes that the prey population will grow exponentially, which is why I had to backtrack on the logistic part. So this is going to grow exponentially and is only limited by the predator, essentially, which is going to be one of the weaknesses in this particular set of models, is that the only thing that's controlling the prey population is a predator, and not competition and other factors that might come around. All right, any questions about the prey model? Okay. All right, then let's look at the predator model. So here's the predatory model. And superficially, it doesn't look as clean or as representative, I guess, of the exponential growth model as the prey model did, but it is still an exponential growth model, with the only constraint being how efficiently they can capture prey and turn them into new predators. And I'll get more to that in just a minute. And so in this one, we've got d N-pred over dt, so instantaneous change in the population size of predators over an instantaneous change in time, equals b which represents the efficiency of converting kills into new predators. In other words, it's not a regular birth rate, right? It's saying that the only way that you get new predators, the only way that you have new predators added is by converting prey into predators. So that's the B. So be careful, not a standard birth rate. Then we have our C, inpred, in prey, which is our predator efficiency, constrained by how many predators there are and how many prey are available to them. And then we have minus D, inpred. And so D here, again, isn't just your typical death rate, but it is the death rate of predators if they can't find prey. So it's assuming the only reason why predators die is because they can't find something to eat. A little bit simplistic, which is what we'll talk about on Wednesday, is it's a simplistic model. All right, so if you think about what a exponential growth model is, it is dn over dt equals rn, right? That's what it is. And so we don't see r obviously in this equation. Yep, but it is there. And so is rpred included in the equation? And it is. It's b minus d. If you go back to your notes before exam 2, you'd find a place where we say r equals b minus d. And so if you look at it from that standpoint, you have dn over dt, r times n. It's still an exponential growth model. Okay, just not as obviously an exponential growth model. Okay. Everybody see that? Okay. And so this equation assumes that the reproduction and death, for that matter, of predators is completely tied to whether or not they can find, capture, kill prey. And that's it. We're not going to work with these mathematically. I want you to understand the different parts, what they represent, kind of like we did for competition models. And then we're going to look at how they work graphically. We're going to look at how they work graphically 2 ways. Okay. And so if you run these 2 models together and you graph them as the number, the population size, and by now you know I'd rather have in prey on one axis and in pred on the other axis because we're running 2 things at once, right? What they choose to do instead is kind of put the arrows and things. But we're looking at the number and time. So that's not what we did last time. Last time we had N1 and N2, right? So we're going to do that on the next slide. But this one is just looking at the number of prey and the number of predators as these 2 models run. What happens to that over time? And so what we're going to see, I'm going to go ahead and get this up, as I've got it written out, hopefully where it makes sense, but I probably won't follow it too much. But what we're going to see is if we start here, when the predator population is low, that means they're not eating very many prey just because there's not very many predators around, and the prey population will grow. All right. At some point, the prey population is going to get high enough that the predators are going to be able to find them more efficiently, and then the predator population will also start to grow. Okay, so that's happening right here. Both populations are growing. All right. At some point, we're going to pass a threshold where the predators are taking more prey than the prey are able to add back to the population. In other words, the death rate of the prey is going to be higher than their birth rate. And that's going to cause the prey to start to decrease. And what this model does is it predicts that the predators will still increase for just a little bit because they don't realize that the prey are declining. So there's a delay here. But at some point, the prey is going to get down to a population size where it becomes harder for the predator to find them. And so then the predator population will start to decrease. And then as the predator population decreases, it's going to reach a threshold at some point. in which the prey are going to be able to begin reproducing again. They don't have as many predators eating them, and so then the prey population starts to come back up, and the whole thing starts over. So it's often referred to as an oscillation or a cycle that's going on. And so you could take this, and this is the same as this, and this is the same as this, essentially. We're okay so far? All right. And I will say, though, when you look at models like this that you get out of a textbook, they are a little bit misleading because there's no way that this many prey are going to feed this many predators. Okay. In other words, your prey population should be really spiky, and your predator population should be much lower continuously. And so this one's a little better. That's why I put this one in. And so it's a little better, showing you that you're going to always have way more rabbits than you have. I don't know what that is. What do y'all think? Coyote? Doesn't look like a fox or a wolf. But you have far less predators than you actually have prey. And if you get on and you look at some of the ones that have actual data from the field, a lot of times they have to adjust this scale to be able to get the peaks in the prey population to be on the graph and still have enough scale down here to be able to see the peaks in the predator population. So that's just a natural fact, right? And so if you have something that eats mice, you know, like snakes, you're only going to have a few snakes per acre, but you're going to have tons of mice per acre is what I'm saying, right? And so just keep that in mind when you see this in a textbook. That's just not realistic, okay? All right. Now we're going to model it ourselves, and I'm going to go ahead and turn this off. You have one in your notes, I think, but we're going to draw it a little bit differently to match the way we were drawing it last week. Okay? All right, I'm gonna get it in front of me. It's right here in front of me. Actually, let me close this so that this is the only thing I'm looking at. So that hopefully I'll keep us in line. So the graph that we just looked at was population size and how it's changing over time. And that's what gave us those humps, and that most people actually interpret that as the oscillation, but we're actually going to draw the oscillation. Because an oscillation means you go in a circle. All right, so that's what's going to happen in our graph. Spoiler alert, we're going to go in a big circle. All right? Just like we did last time, because we've got two models, one for the predator, one for the prey, and we're going to run them at the same time. What we really want to do is we want to have a graph in which we have the population size of one species along one axis and the other species along the other one, so that I stay with my cheat sheet. We're going to have N prey along the x-axis, and we're going to have N pred along the y-axis. Okay, so this gets us back into the mode we were in last week. So this is basically species 1 and species 2, except in this time this is the prey and this is the predator. All right. One of the things that these two models do is it says that the prey population is completely dependent upon the number of predators in the population. Because of that, we're going to end up with a zero growth line that goes like this. Okay? And so this is going to represent all along this line a situation in which our prey equals 0. So that's our zero growth line for the prey. Try not to screw it up. Before we go any further, let's think about why. Okay? Because our model says that if the predator population is low, then they're not capturing and eating very many prey, and their population is able to grow. In other words, everywhere below this line, no matter where we look, our prey is going to be positive. And then our model says that if the predator population gets high, then it's eating an extremely large amount of prey, and that's going to stop the population growth and cause it to decline. And therefore, above this line, our prey is going to be negative. So everywhere below this line, our prey is positive. Everywhere above this line, our prey is negative. Let's do one more thing. Rather than doing it separately like we did last time, let's think about the way that our prey is moving along the axis. Since it's on the x-axis, it's moving this way, right? And so if it's increasing, which direction would our arrow go? This way. And if it's decreasing, which way would it go? Back the other way. Okay, so we've got a lot over here on the side to help us. So far, so good? All right. And so for the predator, so we're looking at the predator now. Probably got too high for my arms, but that's okay. For the predator, the only thing that's going to constrain its population growth is the prey population size, whether it has enough to eat, essentially. And so its zero growth line is going to look like this. I didn't get it very straight. That's it. So this is our pred equals 0 everywhere along this line. All right. So in this case, if the prey population is low, in other words, we're on this side of the line. Be careful not to erase my line. Anywhere on this side of the line, the prey population is too low to support a large number of predators, and our pred's going to be negative. And then on this side of the line, we have tons of prey. The going is good for predators, and so their population will be growing, and our pred will be positive. And what that's going to do for us is we are going to move for predators, since they're on the y-axis, up and down. And so if we're decreasing, we should go down. So let's put our little guide arrow up here. And if we're increasing, we should go up. Whoops. Maybe more straight up. All right. Okay. Did I screw anything up, or are we good? I think we're good. Looks like we matched my model pretty good. All right, then all you have to do is figure out what's happening in each one of these squares. That's all that's left. So let's say I start right here. Kind of like always, since this is a learning exercise, we'll say what our R, do it in the same order as I do it. R prey, R pred. It's going to be, in this case, we are below this line for the predator, so they're decreasing, and we are below this line for the prey, so they're increasing. So that means the predator is going to be decreasing or going down, and the prey is going to be increasing, and overall we're moving in this direction. All right, we'll just go in a circle here. So in this box right here, our prey, our pred, we are still below the line for the prey, and so they're still positive, but now we are on this side of the line for the predator, and so it is also positive. So everybody's happy here. Everybody's growing. And so if we start our little dot right here, predators increasing, prey is increasing. We average those lines. We're moving in this direction. I did that more quickly. Any question? Okay, I'll keep going. Oh no, I have no room. All right, now we'll do this box. All right, and this box, let's see, there's the predator, we're on this side, so it's positive for the predator. We're above this line for the prey, so that's gonna be negative. We'll start right here. The prey is decreasing, predator increasing. Going in this way. I got it. Checking to make sure. And then finally our last box. Alright, so here's our prey line. We're above it, so prey is negative. Here's our predator line. We are below it. Oh, everybody's unhappy. Everybody's declining. So we started out right here, predator decreasing. Didn't need to leave myself enough room really. And prey also decreasing. Like this. Okay, it's all up there. Whew. Stretch my arms for the day. Any questions about what I have up there so far? Alright, so on your homework, I'm going to ask you basically to do this. That's why I didn't give it to you, so I want you to do it again, basically, so you can remember it. But if you do this, now I'm going to mess it up, okay? If I start here, I'm still going up, right? If I start here, I'm going this way. If I start here, I'm going this way. And essentially what's going to happen, and what you see in your homework, is no matter where you start on this graph, you're just going in a big circle. Around and around and around and around. And that's the actual oscillation that they're referring to. It's actually this. Okay. All right. Any questions? Okay. Trying to think if there's anything else I want to tell you today. So on Wednesday,